this is the history of the atomic model. Slides in gray are not tested, but they're important to get an understanding. So I'll be moving through those really fast. All right. So Aristotle and Democritus were the Greeks that lived a long time ago that came up with it, with sort of the idea of the first atoms, but it was more of a philosophy, not really science. The alchemists really worked a long time, but they didn't gain a whole lot more understanding trying to turn cheap metals into gold. That's awesome. Robert Boyle was the first person to really kind of bring something new, but and then we'll skip to phlogiston theory, where they thought that matter would actually disappear because it had lost its phlogiston. So, and Joseph Priestley worked with that to create oxygen. That was really the first element really discovered. And Antoine Lavoisier was the person who named it. He actually made some quantitative procedures, and he came up with the law of conservation of mass. This slide should be in white because the law of conservation of mass is tested. See there it is. If when you understand this, please understand that the law of conservation of mass means that matter cannot be created or destroyed, right? It's not something that is something we can't violate at all, and it's kind of tricky to actually really understand in the lab. It's easy to just say to write it down on a test question, but in a lab is you really need to keep this in the back of your mind. Uh, the law of definite proportions is a given compound always contains the same proportion as the elements by mass. So, there's an example of this I'm going to post. Uh, if we had a bunch of molecules of water in different amounts, they would have the same proportion of hydrogen in each sample of water. Always 2 parts hydrogen and 1 part oxygen. This is an example of the law of definite proportions. It's on page 74, and it's problem number 37. So give this problem a read, pause it, and make sure you understand it. When we have this problem, you might have looked to here and said, hey, they told me chloroform. Well, I don't know what chloroform is, so could I still do this? The answer is yes, you can. All you need to know is that there are 2 different samples and they're both of chloroform. The only difference is they have 2 different masses. So if they're both of chloroform, the percentage of carbon should be the same percentage here as it is here. So we're going to try to find the same percentage of the total mass. If we sum up and find the total mass here, we'll find it out to be 119.41 grams is my total. Since I don't know the masses of chlorine or the masses of hydrogen, if I add these up together, I will get some unknown number. This is actually what we're looking for. It asks you to find the total mass of sample 2. So what I'm going to do is I'm going to apply the mass percent rule by taking the mass percent of carbon and dividing by the total number. And I will get a decimal place because the bottom number is lower and well, is actually greater than the top number. So I want a percentage, so I'm going to multiply it by 100. And when I do that, I come out to be 10.05% carbon. Okay? So if I tried to apply the same thing, and if I left that X in there, I would have 30.0 grams divided by my X value, X grams. That's my total. And this is my carbon. And I still multiply by 100%. I should still have come up with 10.05%. Sorry, that's a little squished, but you guys can see it, right? All right. So when we solve this algebraically, I want you to solve for x, and x will now be 299 grams of chloroform. And that's it. You're done. We found the mass and the total sample. If you wanted to check your answer, take 30.0 grams of carbon and divide it by 299 grams for my total, and I will get 10.05%. So it checks out. Thanks. The law of multiple proportions is also very, very, very important, and it can only be reduced in whole numbers. Here's an example here. When we look at 3 different compounds, and we have our percents of nitrogen and our percents of oxygen, all taken quantitatively. And then if we divide this number by this number, we end up with this number here. So that's not a whole number, but if we compare all 3 samples and we put them all in ratios right here, they're all actually in whole number ratios. This number times 2, a whole number, is this number. This number times 2 is this number. Very nice. So Dalton really is the first one to really make the theory that we start to accept today. Except he thought that molecules were all made up of tiny little marbles. Okay, and the atom was the smallest you could go. So we know now that you can actually you can actually go a little bit farther than an atom. Into the subatomic particles, that protons, neutrons, and electrons. But also, he said that all the atoms were identical. We know now that's not true because we have isotopes. We have the same number of protons, but different numbers of neutrons. So he didn't know about isotopes, but we do now. He also made 2 more postulates that are still hold true today, with the chemical compounds are formed when atoms combine with each other. That's a chemical change, and the chemical reactions involve reorganization. So we still know that as well. He was the first one to actually come up with the table of atomic masses. Mostly he was working with gases, and those were the first real discoveries. And of course with water, with hydrogen and oxygen. So 2 more guys that worked with gases were Gay-Lussac and Avogadro, and everybody knows Avogadro, right? We'll be covering gases a lot more in chapter 5, so I'm going to breeze through this pretty quickly. But Avogadro's hypothesis is visually shown here when we have our helium, nitrogen, and methane molecules, and they have the same volume, the same pressure, and the same temperature, but they have different amounts of gas. So, or the different masses of gas, but they have the same number of particles. So he actually found that these particles had different masses as well. And that's really why we credit him with the discovery of the mole. So the question for you is, are the densities the same, or are the densities identical to the element? Well, that's right, because the grams divided by liters is our density. So these all have different densities, and you can identify a gas by its density. Gay-Lussac's law is kind of special, and it's visually shown here when we have two volumes of hydrogen and one volume of oxygen. That will actually make 2 moles of water, or 2 volumes of water. So 2 moles of hydrogen and 1 mole of oxygen will make 2 moles of water. So that's how they who was able to show, uh, really experiment with the makeup. The part I also want you to take away from this is that volume is very rarely conserved, because of all the empty space that's actually available there. So please understand that volume, it doesn't have to be conserved. All right, so we get to J.J. Thomson, who really discovered the electron by using what he called by using a cathode ray tube. So this tube would have some kind of gas, and it had an electrical charge on either side, positive and negative charge. And then it was applied through another electrical field, which actually made a magnetic current. And when that happened, the electrons would actually attract to the positive charges. So he found that there was a positive and negative charge within the atom. So he found that it wasn't just these little marbles floating around now, they actually had positive and negative charges with it. He thought they looked like this, like the plum pudding, where the whole cloud was positive and the electrons were stuck in the middle. It's a good guess, but we know now because of Rutherford, which I'll get to in a second. Robert Millikan, his experiment was he was able to find the charge of an actual electron by using an oil droplet experiment. By having this atomizing spray, and he made these oil sprays that would actually fall through this hole, and he was able to observe it through a microscope and also charge the oil with uh, with some X-rays. This created the oils to become ionized, and the negative charges would actually repel off of this negatively charged plate. So they would actually fall slower, or uh, hover, or even bounce back, depending on how many electrons they had. So using this, he was able to find the charge of the electron. Becquerel discovered radioactivity in 1896, and he really discovered the alpha particles. That's going to be important for this guy because Rutherford was able to use alpha particles to shoot them at a piece of gold foil. What he did is he would fire these alpha particles straight down the beam and onto a piece of gold foil. He expected them to go all the way through and maybe to be deflected just a little bit, but some of them were deflected straight back, and this totally shocked him. He equated this to saying, if I fired a shotgun at a piece of tissue paper and having the shell bounce straight back to him. It really shocked him. He reported those results, and we were able to discover that there was actually a nucleus in there. The alpha particles were bouncing off the nucleus instead of going straight through. So about 1 in 8,000th of a time. So I want you guys to do this problem before class. Uh, just I want you to carefully think and pick the best answer that you think, and I want you to support your answer using the claim, evidence, and reasoning. I'll check it in class. It'll be your daily grade, for 0 or 100. So it'll be great. Thank y'all.